Okay, let's see, I do have, all right, so Jay, I think you're first.
Photoelectric interaction.
Photoelectric interactions.
X-rays on that again.
Okay. Melanie, did you have something?
Yeah, the what's it called? The spatial, not the windowing and leveling.
Windowing and leveling. Okay.
I remember, but I just want to.
Windowing was brightness, right?
I think so.
No, that was
Or
contrast.
contrast.
Yeah, and then leveling is brightness.
Okay, and then,
Oh, mine was about, what was it? What were you talking about earlier? We were trying to figure out.
The grid
The-
and how it's useful.
No, or I don't know
Well,
if y'all want to ask that too.
That too, grid.
oh, well, that's
Was
actually
it
going to be this
content?
semester.
Does grid improve
Oh,
image quality or just reduce
it's just like
scattering?
during the
Which one is it?
During the Compton interaction,
Mhm.
the the photon leaves with 2/3, and then what about the Compton electron?
Okay. All right. We'll talk about that. All right. Any other topics or any other questions that anyone wants to cover? We can't talk over. We can't discuss everything, right? So I want some specifics. Yes. Emily.
I was gonna say the shade variety.
Shade variety.
Spatial
What's
resolution.
it called?
Okay.
Yeah, that.
Can you go to DQE, MTF?
What'd you call it?
I'm calling it an MTF. Modulation transfer function.
Doesn't, what number goes with that? 12?
MTF.
And DQE.
MTF is what?
Modulation transfer function.
There's a number that goes with that. What is it? 12?
The
15?
number of
15?
Should it increase
20?
or decrease?
Oh.
All right. So how's this feel? Does this feel like we cover pretty much the topics we're not certain about?
No, like attenuation, you might want to go over that again.
Okay,
Appreciate
attenuation.
you.
Mm-hmm.
And heel effect.
Yeah, the line focus principle.
You know,
You might as well go
Everything
around.
about last
You going
semester.
chapter by chapter.
I'm sorry.
all right.
I mean, at least I remember, like,
Thank you,
that this
Mr.
is a
Phung.
thing
Are we
that
gonna be sure that on
exists.
X-ray production?
Oh, you know what else too? The interactions, the Brooms and the characteristics.
Friends and characteristics.
Yeah,
Like cascade.
and not the, see, I don't even know the name of this, but I'm gonna tell you. The chart that we went over, it's called the,
Yes, what is that chart called?
I can't-
Emission
The
spectrum?
Emission
Spectrum?
Yeah, right there.
Very good.
There you go, Veronica. I heard you.
I heard Veronica though. That's
Take picture of that because I'm gonna go home. and-
Move it to the left or right.
Sorry,
It's
go
one of
ahead.
these. I know
All
it's
right,
not up
let's
and
see.
down.
We'll try to cover as many of these topics as we can.
Okay.
That part.
All right. So let's go ahead and start with anode Hue effect and line focus principle.
Yes.
Okay. So why do we have, right? And you see I grouped these two together. What characteristic about the anode, or what characteristic about the target, is responsible for both of these, both anode Hue effect and line focus principle? What is it about the anode that causes that to happen?
Positioning?
Oh, I do.
Are you talking about inside of the two?
Yes, I'm talking about
Oh.
inside the tube.
Oh,
What is it
oh.
about the anode?
Okay.
What is it
so
about the
let's
target
It's the
that causes
Let's start
these
there.
two to occur?
target angle. Right?
The target angle.
That's what I said.
I apologize, I didn't hear you. You're not louder. Okay, so yes, it is the target angle that causes that. Alright? Right? Because if you think about our target, right? Whoops. So if this is our target, right? Our target is not a flat. Whoa, come on, mouse. Okay, our target is not flat like this, right? Our target actually looks like this, right? There is an angle. And so when the X-ray beams come in, so when our X-rays come in, they are dealing with this slanted anode here. Okay? So, because of this anode, we have anode Hale effect, and we have the line focus principle. Let's first talk about line focus principle. So, right now, right, so this was this beam here, right, this beam in red. What is inside this red beam? What is shooting across here? What's going on?
Electrons.
That's right, these are electrons shooting across, right?
Mhm.
Where did the electrons come from, this green thing?
From the cathodes.
Specifically,
The
what part of the
filament.
cathode? Filament, yes. So, over here, right, we have the filament. Alright, so over here we've got the filament, right? And over here, these are our electrons. And so they come over here and they reach the anode. And if we take a look at the anode here, these electrons cover this area of our anode, this area of our target. This purple line here is slightly bigger than the green filament, right? So the filament covers this amount of area, but by the time it reaches the target, it covers slightly more. So what do we call this purple area? So this is on the target, but the specific area, this specific area covered that's slightly larger than the filament.
Oh,
So I'm
focal
talking about a
spot.
focal spot.
Oh.
But which focal spot am I talking about? So there's two kinds of focal spots, right?
Rotating anode.
That's on the focal.
Yeah, that's focal track.
Stationary.
Okay, so yes, that's true. We have rotating and stationary, right? So if it's stationary, right, it is literally a spot. If it's rotating, that spot gets dragged out into a track. Okay. But maybe this might help. If you were to look at this purple area from the viewpoint of the patient, right? So the patient is, somewhere down here, right? So you will give them a nose. Let's make the nose a bit thicker. Right there. Or we'll give them a nose, right? And then here's their body over here. Right, yeah. Right, okay, here's their legs, right? Got their little feet right there, right? So there's our patient, right? And they're staring up at this target. What does the patient see? Well, the patient is going to see this target, and this is what the patient sees. Right? So, he doesn't see this big, wide, or she doesn't see this big, wide purple thing. Only sees this area right here. So I'll go ahead and make that orange. This is all our patient sees, this orange line. So, comparing the purple to the orange, what's the difference between them?
It's small.
Yeah, the orange one's smaller than the purple, right? So, what kind of focal
Is it effective?
versus
Actual.
actual? Very good. So over here we have our effective focal spot size, right?
Yes.
And up top here we have our actual focal spot size.
Like, why is this important?
What is that?
Like, why is this important again? I know it's something, but I just can't remember exactly.
Right, so the fact that we have this actual focal spot size, this actual focal spot is going to determine a certain property about this anode and this tube.
Right.
It's going to determine how much heat it is able to handle. Right, the bigger this area, right, the more spread out the X-rays are,
It can
then it can withstand more heating. right? So more heat can take place over a wider area because you're spreading the heat out. If this was a small actual focal spot size, then you wouldn't be able to heat it for as long before it starts to melt the anode. Okay, so by increasing the size, you increase the heat capacity. The anode is able to take longer or more intensive exposures. So if this was small, it would be hard to do something like an abdomen, because an abdomen takes high kVp, it takes high mass. Right? You could do like a finger with a small focal spot size, but not an abdomen. Right? You need a bigger focal spot size to do that.
Is that where the angle comes in?
So that's where the angle comes in. So how can you make this focal spot size bigger? Well, one thing you can do is you can change up the filament, right? Because most focusing cups don't just have a single filament. They have two. What is that called? Dual focus. Good. So if you have a dual focus, right, we might have something like a big filament as well. Right? So filaments, right? So this is dual focus. Okay?
That's when it has two
Right.
filaments.
Correct. Two filaments. Okay. So in the case of our dual focus, right, we would be exposing like this much of the anode instead, right? We would do this entire thing rather than this small thing. So that's one way we can change our focal spot size. And in fact, that's the only way you can change the focal spot size on the fly, right? Patient comes in, you're like, all right, let's change the focal spot size. The only way you can change it at that moment is to change which filament you're using. However, when the tube is being constructed, right, when the manufacturer is trying to decide, okay, what is this tube going to be used for? They can also change the angle on this anode. The bigger the anode, the more stretched out this focal spot size becomes, and then the higher heat capacity it will have. So if you have a really, really small angle, then it's not going to be able to withstand as much heating as something with a bigger angle. So that's your line focus principle. Right? It depends on two things: the size of your filament and the angle of your anode. Those two properties will determine the size of this actual focal spot size, which will determine the heating capacity. That will also determine down here the effective focal spot size. This determines your sharpness. This determines how much blurriness there's going to be. This determines some of your image quality. Okay, so this is related to sharpness, blurriness, and image quality. Okay, so you do need to know both of these focal spot sizes. Both of these are affected by angle. Both of these are affected by the filaments. Right, that is your line focus principle.
You said it's affected by the angle and what?
So it's affected by the angle and the size of the filament, which filament you've chosen.
So you said what?
The size of the actual focal spot and the size of the effective focal spot.
Is affected by the angle.
Correct. So, in summary, right?
Yeah.
Line focus principle, two variables, right, which is filament size and anode angle. Affects actual and effective focal spot sizes. Effective focal spot over here, right? This affects sharpness or blurriness. And then actual focal spot size up top here affects how much heating anode can take. Okay.
How do they change the angle? Like, what do they do?
So that'll just be during construction of the tube.
Okay.
So when they're making the actual anode, they will determine how much angle to put on there.
So once it's set, it can't be changed.
Correct, it cannot be changed.
Okay, so the angle can't, but the filament
The filament can, yes. So that's why I'm saying, when you're actually working with the patient, the only thing you can change is the filament, right? That's the only thing you can change on the fly. During construction, that's when they can change the angle of the anode.
And then I remember about this that I can't really like remember exactly what you had said, but you
Mhm.
did mention last time that you said the bigger the angle, the
Mhm.
more heat resistance, but the lower the image quality. Is that
But
what you had said?
the bigger angle equals,
I'm not sure if
Larger
that's
the
right
angle,
though.
the larger the amount of heat it can take, and the larger the depth of focus possible.
The angle, what angle?
The targeting.
very good.
So I was right?
Yes. Are we okay with line focus principle here?
Yeah, but give me 1 second because the mic is on.
So we can only change, the filament
Correct.
at the, on computer?
Correct. So at the console, all you can change is the filament. The manufacturer is the one that determines the angle size.
I've never seen them change.
You've never seen the text change the focal spot size? So that's usually because when you are at the console, one of the first things you do is you select the body part that you're imaging, right? And so, when you do that, the console will basically set everything you need for you. Right? When you click that, it sets you a default KVP. It sets you a default mass. It sets you a default AEC, right? Maybe it's on, maybe it's off. If it's on, maybe it selects the outside cells, maybe it selects the inside cells. And then it'll also select a default focal spot for you. Okay? So the console, the computer is actually doing a lot of this behind the scenes for you. Now, if you disagree with what the computer is doing, you have the option to change it. Right? So if you're dealing with a really small patient, like maybe you're doing a PD abdomen, then you can be like, yeah, this PD abdomen is not going to need such high techniques. I could actually use a small focal spot size and low KVP, low mass. But you can change the stuff on the console in that case. So that's if you want to be a really good tech, right? If you want to create optimal images. So once again, as a tech, your priorities will change depending on your patient and where you work, right? Or just the conditions at the time. Sometimes your priorities are, all right, I've got 5 patients waiting for me, I've got to get these done fast, right? Sometimes you're like, oh, I've got no patients scheduled for the next hour, I can take my time with this patient, I can try and get a better picture. Okay? So it all depends on your priorities. If you are prioritizing a better picture, then there's all of these details that you can work with, all these details that you can adjust to create the best image possible. Yes, Melody.
If you want a sharper image, then we just do the opposite.
Correct. So
Smaller focal and smaller effect size.
very good. Sharp image, small focal spot size. Yes, Cody.
What determines why they would make, like when they're putting the, like when they're constructing it? Do you know what determines like why they choose a certain angle?
So, for example, it may be that the machine is meant for a specific application. So if your machine is meant for a low dose environment, low technique environment, you don't expect to be using over like 70 kVp consistently, then you would maybe use a smaller angle because you don't expect as much heating to occur. If you notice it's going to be a tube that's used for general purposes, you're going to be doing pelvis and spine and abdomen on it, then probably aim towards a larger angle and give them more options with the filaments. Good question.
I remember whenever we were first learning about this, or maybe I'm wrong. This had nothing, like, did this lead into like doing, well, maybe not, the filters?
The filters. So this doesn't have anything to do with filters directly, no.
Not directly.
I mean, they're all in kind of like the same area,
Yeah.
right? So we were talking about the tube, we were talking about the anode, and then the filters were coming right afterwards.
Yeah.
Okay, good. So, in that case, let's talk about anode Gill effect. So, let's go and save this. I like this picture. Feel pretty proud about it.
And what is this called?
Line focus.
So this is line focus principle.
Line focus principle.
Okay. So anode Gill effect. We'll just get rid of all this stuff, all this stuff. All that. Okay. Close enough. We've got our anode again. So if we're looking at this anode here, right? And once again, we have electrons, right, shooting across this way and hitting our anode. What is happening here at the actual focal spot? What is happening when the electrons interact with the anode here?
They go one
Is it bouncing?
yeah, one goes to the anode and the other goes to the cathode. Most of it goes to the cathode.
All right, so something's going towards the anode, something's going towards the cathode. Right, there is heating taking place as well, right? Because heat is a byproduct of X-ray production, right? 99% of our interactions actually just produce heat rather than X-rays. Okay, but well, I kind of gave you the answer. What specifically is happening here? It is X-ray production, right? Because we have heating and we have X-ray production. And so what is it that's going towards the cathode and the anode sides of the patient? Those are the X-rays. So X-rays are being created here inside this purple area. So I'm gonna make some X-rays here, right? So X-rays are shooting out from all over, right? They're coming out this way, they're coming out this way, right? We've got leakage radiation
Oh, we
going
didn't do
on.
that picture.
Right, that's right. You guys did a drawing of this for me, all right? So anode Gill effect, right? Things are shooting out all over the place. Pew, 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 right? Except, you notice that some of these lines are traveling through the anode here, right? Some of these lines are traveling through the anode. What is the anode made of? Tungsten. What else? Rhenium and molybdenum. Good. What are those?
Metals.
They're metals, right? Generally speaking, what do metals do to X-rays? Don't say reflect. X-rays do not reflect. Absorb, yes. Right? So what can happen to X-rays? They can transmit, they can absorb, or they can scatter. Do not say reflect. X-rays do not reflect. Okay? So they can transmit, absorb, and scatter. But metals, right, generally will attenuate X-rays. They will absorb or they will scatter X-rays. They do not let X-rays pass through very easily. So our anode here is made of metal. You created X-rays inside the metal. It's now trying to get out of the metal by passing through more metal. Are the X-rays going to make it through? Not very easily, right? So it's going to be hard for X-rays to come out this way. It's going to be hard for X-rays to come out this way. And so what you find is that on the side with air, X-rays have an easy time traveling this way. On the side with the metal, X-rays are getting attenuated, they're getting absorbed, they're getting scattered, and they're not really passing through this way as easily. So, more X-rays on which end? Cathode end, where the electrons are coming from. Fewer X-rays on which end? Anode. Okay, the side of the target, right? So, more X-rays on the cathode end, fewer X-rays on the anode end. So if you have a patient with anatomy that has differing thickness, thicker on one end, thinner on the other, right? Most common example, the foot. If you were trying to X-ray the patient's foot, where would you put the toes? Where would you put the heel?
The heel on the cathode
anode.
side.
Okay, heel on the cathode side, and toes on the anode. And why is that?
Because you don't wanna burn out the toes or some more.
Cause then it's
X-rays
just
on the two after.
All right.
What
Good.
you get, Mr. Phung?
Heel is thicker. We don't want to burn out the toes, right? So more X-rays on the cathode side will help penetrate that thick anatomy, demonstrate it better. Fewer X-rays here, keep ourselves from burning out the toes, so everything looks nice and uniform. Great job, everyone. Great job. That's the end of the office.
Are you proud of that?
I am proud. I am proud. I'm glad that you remembered the activity that you did as well.
So that's all we need to know for the annual effect to put the
Scatter.
stick, for the annual, fuel effect, just to remember that the one with the thicker sheaves otherwise they'll burn out.
Correct. Now, there is one more thing related to the anode heel effect, and it also comes back to sharpness. But I don't want to discuss it just yet. I think we're going to hit upon it later in this semester. So we're not going to worry about that just yet. So let's move on to our next topic.
I hate when you bring stuff up and then be like, you know what? We're gonna say that for
Okay.
later.
All right. Grams versus characteristics. Okay, so.
No.
All right, pass this down, please. Pass this down, please.
I don't want it. He can keep it.
Thank you.
Alright, great. So yes, for this one, you're all going to draw together, right? So I was drawing by myself earlier, now let's all draw together. Yay! Okay, so, not a pop quiz, don't worry.
my sketching pencil.
Well then, maybe I'll give you the pop quiz instead. Just kidding, right? So,
I work good under stress. Go ahead.
we're good in the stress. Alright.
$10.
So here, I'm going to draw two atoms, right? I'm going to draw some circles here.
Shall we draw that?
You want us to
Go ahead and
draw?
draw this. Yeah, go ahead.
But then sometimes you erase stuff too.
I do, that's true.
Don't do that now. We'll wait till he finishes though.
Alright.
And then you
You can wait a bit then, sure. Alright, but I'm going to draw some circles. And what are these circles representing?
the shells.
Like seashells?
No, the digital board. Oh, yeah.
Bohr model. What on earth is a Bohr model?
We learned that today.
Oh, you learned that today in Miss Bonita's class.
We
Great.
did. We did.
What is the Bohr model?
It's where.
He modified
It was
something.
founded in 1913. That's all I know.
Yes, Jay, go ahead.
The Bohr model is a solar system type model.
Solar system type model.
Yeah.
That was from Erding.
Like it has a nucleus.
The solar
and stuff
system-
outside.
The solar system was Erding.
Get in her.
How many circles you got? What's going on?
Oh, for real?
I've got 6 circles here.
Six.
And then a final tiny circle in the middle.
7.
So we need 7.
So we need 7?
Yeah, so yeah, go ahead and draw.
Really, Mr.
7
Flower?
circles. And I'm going to label this middle circle with an N.
Neutron? Nucleus.
Yes, this is the nucleus.
Neutron?
No, not Jimmy Neutron.
And proton.
What? Neutron? What?
You mean Neutron?
Not him.
Not that guy.
They don't know nothing about that.
Okay.
Alright.
See how it's perfect.
7?
Oh, they are not going to.
Doesn't have to be perfect as long as you can understand what you're doing. And so these were shells, you said. What kind of shells?
Electron shells.
Electron shells, great. Do they have names?
Yes, elemental.
Elemental P?
Oh, K-L-M and P.
K elemental P?
K-L-M-N-O-P.
So what letter do we start with, guys?
K.
K.
K. Very good. Right, so we've got K, L,
I'll take these pins back to Walmart. No sé, what I was gonna
Okay, right, K on the B. Here we go. Got our shells. Okay, hold on. Let's make this a bit better. We can make this a bit better. You're better than this. There we go. Now we can do this.
My circle looks so sad.
Mine are lopsided. Half.
And you said put it in?
So,
It's just
or
a
nucleus, however you want to label that. Right? You can just say, just write it out. You can write nucleus. That's fine. However you want, as long as you understand, as long as you remember what is what. Great. So, this is taking place inside the target right now. And where's the target located?
In the anode side.
On the anode side of the tube. Very good. Okay, so the target on the anode side of the tube. So, because this is taking place inside the tube, what is coming in to cause these interactions?
Electrons.
Okay, voltage is creating the energy needed for the electrons to travel from the cathode to anode and interact with these atoms. Good.
What are we talking about though?
So right now we're going to talk about Bremsen characteristic.
Okay.
Sorry, I guess I should forget. So talking about Bremsen characteristic right now. Okay. So yes, the incoming thing here is an electron. It is an incident electron because the electron comes from where?
From the cathode.
From the
Filament.
cathode, specifically the filament. How did it come from the filament? What happened at the filament? Thermionic emission. Why did the electrons stay around the filament instead of leaving?
Or because the cups are focusing cup.
Yes, because there's a focusing cup surrounding it. And how does the focusing cup keep the electrons inside?
Space charge.
Right, there's a space charge, and there's also electrostatic repulsion. Very good.
What is the electrostatic
Wait,
repulsion
say
that
that
is
again?
We
inside
talked about that
the
earlier,
electrons
right?
there?
Yes,
It has a more negative, higher negative charge that keeps it in.
very good. So the focusing cup has a high negative charge. Electrons are negative. They don't like other negative charges. So the focusing cup pushes them back towards the filament. Very good. Great. So, will we ever talk about an incident photon when dealing with characteristic or Brems?
No.
No. So if you see a photon comes in, kicks off the K shell, gives you a characteristic, is that true?
No.
No. What comes in to kick off the K shell?
Electron comes in.
An electron comes in. Very good. So,
You said this happens outside the tube?
so this is inside the tube, anode.
There's something that happens outside.
Yeah,
There's
that's
stuff
like
happening
that's
outside the tube,
Compton,
yes.
the interaction. Compton.
Alright, so we've got electrons here. There's a lot of them. There's like 80 of, no, or like 74 electrons. Right? I'm not going to draw out all 74 electrons, so just have 6 electrons here right now. And so, an X-ray comes in from the outside, correct?
Mm-hmm.
No, from the
Yes,
outside.
an incident.
Yes, sir.
Incident X-ray comes in, right?
No, electron.
Electron,
Yes.
good. Right, so an incident electron is coming in. Let's see, which way, yeah, I'll make it simple for them, that's fine. All right, so incident X-ray comes in, right?
So why do you call it X-ray sometimes and electron sometimes?
Because I'm testing you. So this is our incident X-ray.
Incident electrons.
Thank you, incident electron. Come on, guys.
What's so funny? You're killing me.
I'm sorry. All right, so incident electron comes in, right?
Right?
crashes into the electron here in the K shell.
Yep.
And what happens to this K shell electron here?
It's kicked out.
It gets kicked out. It gets ejected. It was fired, or it left on vacation, right? So it goes away, right? So there is our old K shell electron, and it has gone away, right? So it's not here anymore. Gone. Deleted, right?
Disappeared.
Disappeared. Off somewhere into the target.
Come on, you got some more. Keep 'em coming.
So, how is it able to kick out the K shell electron?
Because it has more energy than the K shell electron.
Okay, how much energy?
More than
69.
Wait, what are we talking about? Characteristics or brain?
This is characteristic.
Okay, characteristics
So,
is 60.
more than how
Yeah,
much?
70 kVp.
69.
69.5 what? KeV. Very good. If you're gonna memorize a number, make sure you memorize that number.
Yeah.
There's a lot of numbers.
That's true, there are a lot of numbers to memorize. Okay, why? Because this is the binding energy of the K shell, right? Okay, good. So, now that this electron is gone, what happens?
Characteristic
Cascades.
Cascade.
Okay, characteristic cascade. What is that?
They start
I know
firing
the-
down.
The outer
the
shell
holes.
electrons move into the vacant.
All right, outer shell electrons start moving in, bloop, 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 falling down into the K shell. Do they have to go in order?
No.
Yes, I thought yes.
No, they do not have to go in order. So, L can go to K, right?
Yeah.
But N can also go.
But P could also go all the way to K.
Oh, it just has to be.
Like skipping was
I thought it was the
ready to
money
be-
like-
thing.
You can
Remember?
skip.
Like,
L
you don't
has
have
to
enough
go to
money, you
K,
can't move
N can
into
go to
the-
K.
Yeah.
Can go to K.
You did say.
I have a question.
I thought that's how it went.
So, the money thing is when you have, so I used a lot of money analogies now that I think about it.
But it's okay,
No,
though,
if
I'm
I
talking
can
about
skip
it.
over,
We
we
get
get it, we get it.
The
Right.
one we said up there about the mansion. You have a mansion, you have a tent, you have
Right.
a regular house.
Yes, that's right.
Okay.
Okay, so, basically, right,
P shall they have enough money?
person could be living here, right? Pretty nice house, but they want to move into the mansion. Okay? So, what's gonna happen? It's like they've gotta pay the landlord, right? Gotta pay the landlord money to move in. So they're like, all right, well, I'm gonna sell my house here and I'm gonna move in. Landlord's like, well, you're short some money, right? Gotta pay up a little bit more. So how much does he have to pay? He has to pay the difference between the prices in these two, right? This is a high-priced house, 69.5. This is a medium-priced house, like
58.4.
it's like 12 point something, right?
Oh, that much of a difference.
Yeah, it's like 12.3. It's like, all right, well, I sold my house for 12.3. I still need some money. I need like 50 something money to pay the landlord to move in. So, okay, pays out 50 something KeV. That's the photon which comes out. On the other hand, person living out in this ramshackle tent on this side of the highway, right? They're like, all right, well, my tent is worth 0.01 KeV. I'll sell my 0.01 KeV tent. Then we're like, yeah, you still gotta pay up. Gotta pay up like 69.499. Like, oh, that's a lot of money.
Where do they get the money from?
They had it. They had it.
It just won't eat.
They had the potential. They had the potential to earn
That's-
money.
then it's-
So they earned the money. So they earned the money. They pay the landlord and they jump in. And so the photon that's produced is now a higher energy value because there's a bigger difference in the prices between these two compared to these two. So any of them can jump in. It's just that when they jump in, they will be giving off more energy. They're paying off more energy to this environment. It's harder for it to go from here to here compared to here, right? It's right. So you're thinking, it's like, how on earth did a person in a tent suddenly find the money to jump in, right? Maybe they won the lottery, right? It's really hard to win the lottery. So this doesn't happen as often. This is much more common, right? Person already had money if they were living here. So they were able to jump in a lot easier. So more often than not, right? The most common thing that happens is yes, they'll go in order. K is gone, so L goes to K, M goes to L, N goes to M, O goes to N, P goes to O, right? That's gonna be the most common thing that happens. But in other occasions, on more rare occasions, you will have M or N or even O and P all the way out here jumping into the K directly. Okay? And so when that happens, they give off higher energies. Does that make sense?
And that energy that is given off is the photons.
That's the photon. Because what is a photon?
Energy.
Packet of energy.
A packet of energy, okay? If you're gonna memorize the definition, memorize a photon as a packet of energy. In fact, Janelle, what is a photon? Just say a packet of energy. A packet of energy. No charge, not positive, not negative. It's just a packet of energy. All right, Charo, what is a photon?
A packet of energy.
A packet of energy, great. Veronica, what is a photon?
Package of energy.
Packet of energy, good. Carla, what is a photon?
Packet of energy.
Packet of energy. Cody, what is a photon? A packet of energy, good. Sindhu, what is a photon? Packet of energy. Shamika, what's a photon? Packet of energy. Hansi, what is a photon?
Packet of energy.
Packet of energy. Reagan, what is a photon?
Packet of energy.
Packet of energy. Melanie, what is a photon? Packet of energy. Emily, what's a photon? Packet of energy. Angelica, what's a photon?
A packet of energy.
Packet of energy.
Can I drink my water?
Shaheen, what's a photon?
It's a packet of energy.
Packet of energy. Jay, what is a photon? An okay. To be honest, it's more of a cardboard box, but I'll let that slide. Johns, what is a photon? Packet of energy. So a photon is merely a packet of energy, right? Has no charge. I didn't say it was a positive packet. I didn't say it was a negative packet, right? No charge. It's just a plain packet of energy. Does it have mass? Does it have volume? Does it weigh anything? No. It's just a packet of energy. That's all it is. It's just plain old pure energy.
So a photon is a packet of energy. Is that in every case? Like anytime we talk about protons, it's just.
Correct.
Are you sure?
That's all we're talking about.
Photons?
Photons are just energy. That's all we're talking about.
Okay. I said proton, you said yeah.
We also say X-ray.
Yes. So just be careful because there's protons as well, right? Protons are different. Make sure that you are using the H one and not the R one.
So,
Yes.
when we say energy is mc squared, but you have mentioned it before. But then that means energy has mass.
No.
Then why we say the mass?
Hey.
That equation tells you you can take pure energy, which has no mass, and you can convert that energy into mass. You destroy the energy to create mass.
Yep.
Oh, it is.
Man.
But energy does not have mass.
Energy does not have mass by itself.
Is photon also synonymous with X-ray?
So, are photons synonymous with X-ray? X-rays are a type of photon, but not all photons are X-rays. So X-rays are a packet of energy. Depending on how much energy that packet has will determine its identity. If it has a high enough energy, it is an X-ray. And it came from outside the nucleus. If it has a high energy and it comes from the nucleus, now that's a gamma photon, a gamma ray photon. If it has lower energy, now it's ultraviolet light photon, or it's visible light photon. Yes?
Okay, so all X-rays are photons, but not all photons. Photons, but not all photons are X-rays, because he said something about ultraviolet and sunlight.
Great question. Why do we have two circles? So on one side, what is this? Characteristics. So on the other side, what are we going to throw here? Brems. Did I draw any electrons in the Brems diagram?
No.
Why not?
Because
They don't have a set number.
It interacts with the nucleus.
Right.
Thank you.
Brems interacts with the nucleus. We don't care about the electrons in the Brems. So we're not going to draw electrons here because we don't care about them. They exist, but we don't care about them. So once again, here comes our incident electron. It passes by all the other electron shells here, and it reaches the nucleus, or just outside the nucleus.
It slows down.
It slows down, and what else happens?
Changes direction.
Changes direction. Ooh, I like that sound effect. That's right. It slows down, it changes directions. What's slowing down and changing directions?
The incident electron.
Incident electron or incident photon?
Electron.
Electron. Very
Don't confuse
good.
me.
Incident electron.
Wait, so the red lines are the electrons?
The incident one
That's
should
right.
be
This is still our incident
specific.
electron.
So please for the checking, you put the photon on that.
Okay.
Photon.
So-
Photon.
No, it's
No,
electron.
meaning right photon, on the thing that is between.
Wait, what?
No, photon.
That's an electron.
No
It's
photon.
electron.
No, so the one that is,
Talk about the
Oh, that's-
characteristics.
This
but
is
is
an
it, this
electron.
also an electron, so after it gets
That's,
cut down?
that was your K-shell electron.
But isn't that a photon?
Sorry, former K-shell electron.
Original, yeah.
Oh,
So, the
And
photon.
not a photon, which is not a photon, so.
That's not a photon. So, where are the photons coming from in these two diagrams?
This,
No, well, yeah.
When electrons are jumping down or
I
when
thought it was from
energy is
the shell
moved
that
or
comes from the
stopped
other
or
shell.
That's right. So,
I'm not following you.
when these electrons move, that's where the photons are coming from. So
okay.
photons are coming from here between K and L, because L jumps down to K, a photon is produced, right? Your cascade. Here,
Secondary photon.
right? These are your secondaries. So when M jumps down to L, boom, photon is produced. When N jumps down to M, boom, photon is produced. O jumps to N, photon. Here, okay, I won't cover it up. P jumps to O, photon. So photons come out when the electrons
The
change
cascade.
shells, when they change houses.
Okay.
Right, that's when they pay to change houses.
Okay.
Those are our photons.
Go ahead and label those.
What, wait, can you repeat that? Photons come out when
They
they jump?
jump shell.
When they jump shells, when they change shells. But no shells are being changed in Browns. So where on earth are photons coming from in this case? Jay, near the nucleus. Why are photons coming out near the nucleus?
Because they're being slowed down.
They're being slowed down. What is
Or
slowing
the
down?
electron is being slowed down and then changing direction.
Okay, so what does slowing down and changing direction have to do with energy?
Good question. I do not know.
Has to be maintained.
We have brain break. All right, let's finish this up then. So, when you slow down, right, you have a certain amount of energy as you're going fast, right? When you slow down, you are losing energy, correct? Where does that energy go?
Heat.
So right, if you're in your car, it goes into heat, right?
Oh.
The brake pads hit the wheels, right? Produces heat. That's where some of the energy is going. Where else does that energy go?
It's screeching, maybe loud.
And then it just
The
goes like
noise.
everywhere?
That's right. Heat, sound, light, right? Energy is being converted from motion into all these other kinds of energy, right? In this case, the electron has energy. It comes here, it slows down. If it's slowing down, it's also losing energy. But the electron doesn't have brake pads, right? The electron doesn't screech when it slows down. So what on earth is that energy being converted to as the electron slows down?
Photon.
It's being converted into a photon, which is a
Packet of energy.
packet of energy.
Is it for,
Remember,
oh, sorry.
if I ever ask what is a photon, you answer
Packet of
Packet of
energy.
energy.
packet of energy. So we're losing energy. What happens to the energy we lost? It gets packed up, stuck into a cardboard box. Sorry, not an envelope, but a cardboard box. And that is our photon. Right? So we lose energy as we slow down. The lost energy gets turned into a photon and it shoots out. So there is our photon. happens when our electron slows down. Right, so let's see. Electron slows down. To slow down, it loses energy. The energy lost takes the form of a photon.
Okay, that makes sense.
Okay. Over here, the electrons change shells, right? Characteristic cascade. Then they change shells. They release a photon.
So, please for a picture, can you put grams on one side and characteristic on
Why
the
does it feel like I'm just learning this for the
Do
first
it
time?
yourself. You guys are drawing
Where are
this.
the pictures?
We wrote characteristic right there, and then the next side where he just typed.
Thank you very much.
Mr. Phung,
Yes.
theoretically on the left,
Yes.
were there 5 photons created?
So yes, here you have a maximum of 5 photons that can be created. What is the minimum number of photons?
6.
1.
Wait, none.
Say your question again?
So if we have the K shell kicked out, the maximum number of photons we can produce is 5. Because 1, 2, 3, 4, 5. But if the K shell is kicked out, what is the minimum number of photons that can be produced? Minimum.
6.
Minimum. Well, maximum is 5.
5.
Minimum is
1.
1.
2.
How do we get only 1 photon out of this?
It's 2.
2. Okay. What are the 2 photons?
Pack of energy.
Is there a way to create only 1 photon here? Yes, there is. When the guy in the tent sells his tent and moves into the mansion.
So it's minimum, right?
So that is the. So the minimum is 1, the maximum is 5.
So why are you
What?
We both said 1.
A lot of people said 1.
Yeah.
Well, I was,
It's okay.
He's like,
I
I
was
was
looking
testing
for,
the other
I was looking
ones.
for more people.
I was testing the
I
other
was
ones.
like,
Because I was hearing all sorts of numbers, right? So I wanted to get more of a consensus.
I'll let you slide.
Thank you. I appreciate that.
Okay,
So
question.
yes,
So if it's a big jump, it's 1.
big jump is 1, small jumps 5. Yes, Reagan.
I remember whenever we were originally learning this, there was one that was more, which one was more, happens more often or more likely to happen?
The small jumps happen more often.
No, I'm saying like between the two, right? Or
Oh, between the 2. Yes, great question. So between characteristic and Bremsstrahlung, which one is more common?
Is it
Bremsstrahlung.
Brems is more common,
Yeah.
Okay.
right?
Because it creates stronger energy photons. The Brems.
So yes, it creates a wider variety of photons. You can get higher energies.
Yeah.
But if you just think about it, right? And you learned about atoms with Miss Bonilla
Yep.
today. So think about, so how big is a proton? Okay, small, right?
Yeah.
How big is a neutron
Small.
compared to a proton?
A little bit.
Very slightly bigger, right? They're about the same size. But the neutron's a bit bigger.
Yep.
What about an electron?
It's a small
I
one.
don't know.
The smallest is tiny. It's like
Okay.
less than, it's like, how do I put this? A proton is like 2,000 times bigger than an electron, right? It's like comparing a beach ball to a ping pong ball, right?
Yeah.
Protons, neutrons, much bigger. Nucleus, right? What is the nucleus?
That's the center of
There's the
that.
protons in the
Right, center of data made of protons and neutrons. So now imagine you've got a whole bunch of beach balls. You've got like 74 beach balls, plus that's your protons, plus however many neutrons, let's say 100 neutrons. So you've got like 174 beach balls all wrapped together. How big is that? Pretty darn big, right?
Yeah.
And now let's say that somewhere a bit further away from your beach ball, you've got a ping pong ball. And now you're throwing things, you're throwing ping pong balls in that direction. What are you more likely to run into? The other ping pong ball or the 100-something beach balls?
The beach ball.
The beach balls, right? So the nucleus is a much bigger target. So when electrons zoom through, they're probably going to miss all of these other electrons and then interact with the nucleus. So BREMS is going to be a lot more common. Make sense?
Perfect.
Things are really small, but if you think about them in terms of scale, right, nucleus is giant compared to a tiny electron.
So to control characteristic happens in with the electrons, and that happens with the nucleus.
With the nucleus. Yes. Then you are right. It is specifically the protons of the nucleus that cause BREMS to happen. All right. Someone said they needed a brain break.
Me.
All right. It's 1:45. We can't take too much of a brain break because I do want to. You guys, yeah, class is about to be over, and I do want to at least cover one more thing on this list. So let's just take a small moment to all stand up. So let's take a small moment to
He can keep teaching through study hall because I need some help. I done forgot.
Friday, are we doing the task of first thing?
Yes. Well, I'll be